In the previous videos, we've considered longitudinal and lateral trim and stability somewhat separately. In general, all of this has to be satisfied at the same time. Your longitudinal and lateral forces and moments all need to sum to zero in order for the aircraft to be trim. So we divided them up so we could understand the dominant features in longitudinal motion and lateral motion. And it helped us hopefully understand the physics of what's going on a little bit better. So for longitudinal, we had the sum of the forces in the x direction and the sum of the forces in the z direction, and the sum of the moments about the y-axis had to be equal to zero. And in the lateral development, we looked at the sum of the moments about the x-axis, the sum of the moments about the z-axis, and the sum of the forces in the y direction, said that had to be equal to zero. Well, these are this is a three-dimensional system, and so we have 6 degrees of freedom. We have forces along each of the axes and then moments about each of the axes. And so if all of this sums to zero, then we're in a trim state. Now, these forces and moments include aerodynamic forces and moments on the aircraft, as well as forces and moments due to thrust. If all of that sums to zero, and also body forces, so like our weight vector, if all of that sums to zero, then the aircraft will be in a trim state. So just as a reminder, from this set of equations, we broke that down into a linear system of equations, assuming that we're at small angles of attack and elevator deflections. So we said that we had some coefficients. So the first equation, actually we broke fx and fz into equations for lift and drag. And we actually dropped the drag equation so we could focus on some of the aerodynamics. Really, the drag equation just tells you what your throttle setting needs to be. So anyway, we decoupled that, and then so we took our top equation here was the lift, and then the bottom equation was the moment. So we had like a change in lift with respect to alpha, a change in lift with respect to delta E, a change in moment with respect to alpha, a change in moment with respect to delta E. And then that equaled everything on the right-hand side, which was all of the stuff when alpha and delta E were set to zero. And so let's see, we had a CL minus CL0 and a minus CM0 over there. Okay, then laterally, we kept all three of these equations. And so we said the top equation was the force in the y direction, and then we had a moment about the x and a moment about the z. And the three variables we looked at there were our side slip angle beta, our delta A, and delta R. And that had to be equal to the negative of the weight coefficient times the sine of our bank angle, and then plus any forces and moments due to the propeller or propulsion system. So we'd have Cy of a propeller or propulsion, Cl due to propulsion, and Cn due to propulsion. So the coefficients that we had was like a change in y with respect to beta, change in y with respect to delta A, and change in y with respect to delta R. And then this was a change in rolling moment with respect to beta, change in rolling moment with respect to delta A, and with respect to delta R, and then the change in yawing moment with respect to beta, delta A, and delta R. Okay, so these were our lateral equations. So we solved these independently, and but this should not make you think that coupling between these longitudinal and lateral is not important. In fact, it's very important. The reason we broke this up was just really to better understand the physics of what's going on. But in general, really what we have is 6 equations. So we could write one big matrix here with 6 equations in it, each of our forces and each of our moments. And then the angles that we could solve for would be our 2 aerodynamic angles, alpha, beta, and then our 3 control surface deflections, delta A, delta E, delta R. And then last we would also be including this drag equation up here, so we'd be able to solve for some throttle setting, okay? And we'd set that equal to everything when these things are 0, so we could have 6 things over here. Anyway, this is really our general set of equations that we would, within linear aerodynamics here again, so we're assuming that that these relationships are linear, so we're at small angles, anyway, this is what we'd really solve in a general sense, and we'll actually cover this later, this more general solution later, when we talk about just a general trim algorithm as part of flight simulation to help trim out an aircraft for a flight simulator. But hopefully what you've gotten out of this is the important components of both longitudinal and lateral trim and stability. And again, these coefficients inside of here, so for example, these are aerodynamic coefficients, as are these. These are control derivatives, aerodynamic derivatives and control derivatives. These are all control derivatives here. And our pitch stability derivative here, actually the ratio between these two tells us the static margin, so that's an important a measurement of longitudinal stability. And then our CL beta is our roll stability derivative, CN beta is a yaw stability derivative, and we've talked about what those need to be. So from these coefficients, we can understand the stability of the aircraft, and we can use the coefficients then to trim the aircraft.